we had incomplete data of the carbon cycle of a forest ecosystem, and the idea that, was that Juan builds a closed carbon budget for us.
Okay, I've been in the BFW for 6 months, as Robert has said. My name is Juan. I was in the Department of Forest Ecology and Soils, and I made a carbon cycle in an ecosystem in Tirol. As a personal introduction, as Robert has said, I have studied forest engineering, and I want to say why I'm here, because I was really interested in renewable energies, because I think that Europe has strong dependence on fossil fuels and using biomass and so, and also the situation in Spain, the devaluation of forests. Perhaps using biomass can recover this value, but unfortunately I don't think so. And then for my personal experience as well, it has been a very good time here in Vienna. I even have learned Deutsch, so this is really cool. Then our motivation and background was several reasons. The first one and the most important is the carbon dioxide. It's a very important greenhouse gas, and also is very relevant for life, very close to the, very strong correlated to the climatic change, as we can see in this graph. And also there are a lot of uncertainties about the future in this topic, and we can see how different could be the scenarios in the future. We have here two different situations of Berg. The first one is a positive feedback loop, in which he says that CO2 in atmosphere is rising and rising, because CO2 will improve the respiration rate and so. And below we have the second negative scenario, in which he says that this CO2 will act as a fertilization of productivity, and then succeeding a decrease in CO2 in atmosphere. We think that we are in the both of them, and knowing how balanced it is the hard work. And then also Kyoto Protocol and whatever policy, because Kyoto Protocol is a little bit questioned nowadays. And I put here the comparison between carbon production and carbon consumption, because I think that is the main mistake of Kyoto Protocol. Only look for carbon production and looking at good Europe, a good looking area, and it didn't take care about carbon consumption. And that's why the sentence I write here from Helm, which says that ETS-EU, which the emission trade scheme, had no sense nowadays, so we have the fixed carbon until 2020 just fixed, already fixed. So there are no price in the carbon chain, the carbon trade. And then other reasons, the unknown of, as Robert says, and the unknown of the decomposition process in the soil, and also our data available we have from measurements from field. Then the site of the study was Ahenkig in Tirol. It's 920 meters above sea level. And we can see here how steep is the mountain, and we have also data about climate, precipitation, temperatures, and so on. We have used it in some calculations in the thesis. And the main tool for doing the project is Stella, which is a software from EC Systems, a North American group. And this software allows you to programming, but without programming. It's really intuitive, really interesting, because you just only use this kind of elements. I have put here one stock, one flux, and one converter, because it's the main elements. Stocks most of times are accumulations, fluxes most of them are process, explaining accumulations, and then you can display these fluxes with converters, with the little one, which explanations. And here we have a typical display of Stella in the model layer, in which you can write at the right part equations and using built-ins, expressions, mathematical, logical, whatever, and writing your equations. You can above you can see that you have several tabs in which you can choose introducing a graph function. You can also here the equation layer is where you can see the programming part that you really are doing but you don't know. That's all. Then the interface layer, I will show it to you later. And this is the value that we wanted to reach. We have a thesis from Mikovic, from BOKU. And we have three main targets. One was the total tree storage. The liter fall was easy to measure at field, more or less. It was 4.5 kilogram hectare year. And the soil respiration, split it 50-50%, was approximately 5 tons. And we wanted to fix all our data with test targets. If we go inside in the model, we have this first shell of the model was 3 modules, and you can with the mouse you can click on them and go inside the model and see the display before. And this is our first attempt. I wanted to reflect it because we spent 1 month, perhaps 1 month and a half, trying to start with GPP, with gross primary production, photosynthesis, but it was really difficult to do that with only a mathematical software, because we don't have time for that. But we simplified the thing and just introducing the temperature and the moonlight and some physiology factors. We could reach a good NPP from a potential GPP with a little low error compared with the reference value. But we couldn't obtain fluxes out these stocks because the model doesn't support that. So it was only useful for that. So finally we started with MPP. This is how it looks, the biomass model at the end. Finally we started with MPP. Here up at the left, and just only was the table, yield table from Achenkig. It's only the current annual increment, and this is how it looks like in Stella. This is the graph, and this is the behavior of MPP, and the blue one is the behavior of stem. A little bit linear, but how it looks like. Then we have 4 stocks, the main stocks of the tree, with stem wood, leaves, fine roots and coarse roots, and it's just only with some coefficients from pits, and we use them compared related with MPP coming to a stem, which is the main inflow. And we have here the problem of the competition between trees, because it's a really difficult thing to do only with mathematical software. And we finally should to fix one lay. This was the result with the gap adjustment. Just only this on the left. It was this is the behavior before the gap adjustment, and the right one is the behavior of the leaf biomass after the gap adjustment, fixing a lay. So quite fixed, but we should do that, because if not, competition must be included, and if not, it was difficult. And then after that, we have fluxes for liter fall from each stock. So coarse roots and stem wood is not included; it's included in the whole plant mortality. But here, stem wood is the all woody above ground biomass. So we extract cones falling and branches falling from stem, and also leaves falling and fine roots falling. We have also a table of liter fall. So we can extract a random factor and so, because there is a building very interesting in Stella who acts as a random. And here we have how it looks like the liter fall contribution of each stock. The first one is needles, which is the main. And on the right part, I pointed out the gap adjustment, because if not, it would imitate the behavior of MPP. And then we have also auxiliary stocks with no physical or important meaning, but we have whole plan, which is the sum of the all elements, and also, but just only for extracting the mortality, was very low. And then the above liter fall sum and the below liter fall sum, just only for separating both parts. And the main thing was the output for introducing in the soil model was total liter fall sum. The target of the work was introducing the temperature effect, knowing or trying to guess which will be the situation in the future. Because previous observations, we know that in 10 years the temperature rises 3 degrees, and this succeeding the productivity rises 30%, and this is how we introduced temperature effect in Stella as a linear function. And this is the interface layer I showed you before, or told you before. You have here all the elements for interacting with the model. There are input device knobs, the most important here, these two. With these two you can modulate the activation of temperature. In the position 0 there is no temperature effect. In the position 1 you are activating the whole temperature effect. And at the top you have another notch that's just only important to the soil model, and there is no point explaining it here. And also we have here the graphs. You can place pages in and see the elements you want, and below there are the numeric displays in which you can see numerical outputs. And then this is, if we go inside to the model, this is the scenario 1 in 100 years, the biomass results. We get very good results, we think, very close to the 80-20 split of biomass in above ground and below ground. And also we got 600 kilogram hectare year of fine roots contribution. It was a data a little bit unknown in the articles we read. Then the errors, and because there is a good error, because it depends on the simulation, because the random building, but we took a good one, and we have a very good liter flow rate. Then big errors, but in nature we know that big errors are relative, and this is how it looks like. The leaf biomass is almost steady state, so it's fine. And then the scenario 2, 3 and 4. The scenario 2 is 100 years and the temperature effect activated. This is a problem we have, because if we didn't allow lay to rise with temperature effect, we would do a very fixed model without no applications for more scenarios, just only 100 and no temperature effect. And we should to introduce a little bit growing of the lay for controlling competition, and that's why leaf biomass increases a little bit, or maybe it rises a lot with time. Scenario 3 is longer simulated, so 1 year and 50, and for the same reason we can see there that the biomass leaves with the red one is decreasing with time. Also we can see a more sigmoid behavior of stem, but also we still that stem behavior should be more pronounced, the sigmoid behavior. So here is a little bit linear. And the liter flow contribution is at the bottom at right. The blue one is the above liter flow contribution, and the red one is the below liter flow contribution, fine roots. And the scenario 4 is the same, but with temperature effect. We can see results similar to the scenario 2, but longer simulated. And then we go to we do a comparison, numerical comparison. Here in this part, in the right part, we have just only values for the 4 scenarios. And in the right part, we have comparisons between them. So the first column is the comparison for 10 years of simulation with and without temperature effect. The second one is the comparison just only taking care about time, so 150 and 100 only. And the third one is the comparison between 150 with temperature and 150 without temperature effect. And I pointed out some values. The first one saying that we can fix more carbon use with temperature. So the fertilization of CO2 is real. And leaf biomass was also high with temperature effect. And also we can see that, above liter fall zone was also liter fall is almost constant with time, but with temperature effect we can see how it increases. And that's all. Then if we go to the soil, we used JDBerjon. We use it because we needed something physical, physiological processes. Just only with the mathematical software, it was really difficult to model soil, and we use it because it allows us that thing. The carbon in soil consists of 4 different compartments: decomposable, resistant plant material, and then bio, which micro biomass, and humics. And each compartment has a exponential first order decay, which pointed out at the right part at the top. And we do something like a equation system, trying to split all things, and we get the relation and the configuration of the whole thing. And this is how it looks like at the end. This is the soil model. Here we have the four stocks: DPM, RPM, bio, humics. Here we have the respiration part of each one. And the right part we have the sum, so total organic carbon and inert organic matter. And that's all. The next thing was to knowing how climatic effect affects to this kind of respirations, and we knew by reading some articles that perhaps precipitation does not affect too much, even less in Achenkirch, because we have a good precipitation, or a big precipitation in the year. So we can see how from the precipitation 100 we have almost a line, so we didn't. And also we can see the B modifying factor, because the decay rate is affected by some factors: A for temperature, B for moisture, C is just only for vegetated or bare soil, and then the K was the main factor. And here we can see how B, which is the factor related, the red one, related with moisture, is almost constant in one. And then we have that the temperature affects more to heterotrophic respiration. Yes, 29% of times explains this increase. And autotrophic respiration was explained. So here we have the temperature effect in heterotrophic respiration, and in the right part we have a correlation. This is an output from the biomass model, just only a weighted mean for fine roots and coarse roots, because fine roots respire at a higher rate, and just only an input of this weighted mean, and it was just affected because the temperature effect in biomass. And then in that part we have stable C and label C that we do with this idea from Zimmerman, who was just only for initialization to stability of carbon soil, and because he saw that a comparison between Roche and this split, so it's Bohm and Dog, is most of times DPM plus RPM is close similar to the sum of BOM and BOC, and also human bio is most of times the same sum that physically protected carbon in soil. So this is the results of the scenario 1, it's the same scenario as before. Here in the first graph we have DPM, which is the blue one, RPM, which is the red one, bio, the purple, and humics is the green. And you can see how DPM is the more variable. Then here we have respirations. We can see how the green one and the orange one was split in 50 and 50 because we forced it in the soil model. And in the right part we have the label carbon, which is the blue, which is almost constant in time, and the red one, which is stable carbon. And then the results above, just for validation of the results. So bio was measured in field and it was a reliable measurement. It's fine. DPM is a little bit low. Also, TOC is a little bit low, and soil respiration was quite lower than we wanted, but in acceptable range. And then in scenarios 2, 3, and 4, here we have that DPM increases with temperature, was a little bit striking, because we expected a different thing, but the little increase covers the increase on the respiration rate of DPM. Here above on the right part we can see that the label carbon decays a little bit, and here we can see how the heterotrophic respiration increased more than autotrophic. Then in scenario 3 we can see the most important thing, that if we don't introduce the temperature effect, so heterotrophic respiration is constant in time, and autotrophic respiration emit mimics the biomass, the root biomass behavior. And the scenario 4 is just the same but longer simulated. From scenario 2, here we can see that again heterotrophic respiration is the same or more or less autotrophic. So here we have the numerical comparisons as with biomass. The main thing is that soil respiration is higher, but higher is with time, because we are like afforestation the place, because we started from a zero situation. So it's logical that with time soil respiration increases, and then we have ppm higher also there, and we have also bio decreases with time and with temperature, and we didn't know, but perhaps if for competition, or this is a mathematical result, but if you wanted to find a physiological one, you may say that perhaps with competition microbes have more activity, and that's why we have more competition. And we can see the main thing that this stable carbon increases a little bit with the temperature effect, but the label is lower. Then we do, this is the general view, and we have the two models, and the third one is balances from the two ones. So we have the three main balances are carbon balance, just only comparing the total MPP and the total soil respiration. The stability balance, which is the comparison between stable and label C, and then the types respiration balance, which is a comparison between heterotrophic and autotrophic. Here is just only an example of equations in Stella. And here we have the results of the balances. We can see in the blue one and the red one, who has carbon balance and type respiration balance, respectively. We can see how we can fix more carbon with temperature effect above in the second scenario, so it has higher values. Also, more stable carbon exists in soil. And here we have a breakpoint, but it was explained because the lay behavior, because we are increasing in the time 25, and the stock of leaves was a conveyor, which means that this material entering now GR0 is leaving the stock in the GR transit time to right. So that's why we have, because the transit time of leaves is 5 years, and that's why we have this breakpoint in the year 25. Because the lay behavior reaches its top level at the year 20. And that's the scenario 3 and 4. We can see the aging of trees, and also stable carbon continue rising. So we can see how temperature effect affects to heterotrophic respiration with temperature. This is just only a graphical view of how increases each balance, the difference. So the red one is the increasing on heterotrophic respiration, the blue one is increasing on the carbon fixed as a whole, and the purple is just only a little bit increment in the proportion of stable carbon in soil. This is the numerical data. It's only seeing that we can fix 50% more in both scenarios, 10 and 100 and 150 years, and also that stable carbon increases in the proportion of stable carbon increases with time, but as a sigmoid behavior we have 22 in the year 100 and 11 in the year 150. Then we do just only fast a monthly model for contrasting things, just only introducing monthly scale, seasonal variations from temperature, from autotrophic respiration, and we just only want to, I want only just to show you, biomass was quite a bit, perhaps a little bit lower the values, but very close to the yearly model. The problem of comparisons of fluxes because the variation, interannual, intermonthly variation. Soil results was like this. More we can see how the blue one, which is the ppm, is we have also like a wave behavior. And we can see humics who reaches the top level before in the year, perhaps, I don't know, the year 30 or 40. And then the thing that, because the main thing doing the monthly model was slowing down the rates of the decay of each compartment in soil, and that's why we have here more label carbon than DPM, but it was just only for compare values for the soil, because it was quite low, our values of the soil, of the carbon in soil, and with model we have higher values and more realistic, but we are suspicious about this behavior. And this is the monthly model with temperature effect, just seeing that label carbon is decreasing, also humics decrease a little bit. We can see at the top that also both stable and label carbon decreases. So, but humics decrease the same as RPM, and that's a little bit strange, we think. And this is the balances results. We can see, as well as the yearly model, that we can fix more carbon with temperature effect. Also, that autotrophic respiration is more sensitive to temperature, and that stable carbon and label carbon decrease both, but label carbon decreases rapidly. So we have the next conclusions. We know that it's still possible to fix carbon with Norway spruce, but for sure it would mean added costs to this kind of forest, but not directly to Norway spruce, but just for insects. So climate change is increasing this habitat for insects, and there would be, or there are just in the moment currently insect attacks, but it would be worse. And also beach, the problem of some invasive species. So we have to study genetic investigation about Norway spruce, adapting it for these attacks for insects. Also periodic analysis of forests, so in wood, how it is evaluating with time, and also markets, the evolution of markets in the sector. Also will be intelligent to have some alternatives for species substitution in private farms, where just there are nowadays damages. And also with this work we can see that there are a lot of unknowns. On the decomposition process we can see that Rothschild doesn't fix very well, because Rothschild was made by croplands, and woodlands is said as such a global term. And also we know that soil respiration will increase, and heterotrophic seems to increase more than autotrophic respiration. And if we see label carbon, we can say that with climatic effect it would decrease in soil. So we are reaching a new equilibrium between label carbon and stable carbon. And the unknown was stable carbon, because we don't know exactly if it would increase or decrease. Perhaps we think that in mature soils there would be a little bit loss of stable carbon, and then in mature soils perhaps we can fix, so there would be a little bit of increase of stable carbon. So there is a term here, the maturity of soil, that we think that is important. And and for ending, the new policies, so taking care about the carbon consumption in policies in a country, trying to design low carbon activities in industries and carbon footprint, and so not only being obsessed with the production of carbon. And just that's all.